Advantages of fuel cells. Now, because fuel cells are factories which produce electricity, as long as they're supplied with fuel, they share some of the characteristics in common with the combustion engines. Now, because the fuel cells are electrochemical cells, electrochemical, energy conversion devices. They rely on the electrochemical or the electrochemistry to work their magic. They share some characteristics common with the primary batteries. In fact, fuel cells combine many of the advantages of both engines and batteries. Since fuel cells produce electricity directly from chemical energy, they are often far more efficient than combustion engines. Fuel cells can be solid state and mechanically idle, means no moving parts. This yields the potential for a high reliable and long lasting systems. A lack of moving parts also means that the fuel cells are silent, and also undesirable products like nitrox and sulfox and the particulate emissions are virtually zero. Unlike batteries, fuel cells allow easy independent scaling between power, which is determined by the fuel cell size, and capacity determined by the fuel cell reservoir size. In batteries, fuel cell and capacity. In batteries, power and capacity are often convoluted. Batteries can scale poorly at large sizes, whereas fuel cells scale well between from 1 watt range, which is a fuel cell, to megawatt range, a power plant. Fuel cells offer potentially higher energy densities than batteries and can be quickly recharged by refueling, whereas batteries must be thrown away or plugged in for time consuming recharge. So this we have a schematic comparison of the fuel cell and batteries and your combustion engines. So fuel cell and battery, in a fuel cell and battery, chemical energy is converted to electrical energy, whereas in a combustion engine, heat energy is converted to your mechanical energy. Chemical energy is converted to heat energy. Heat energy is converted to mechanical energy, which is converted to an electrical energy. Whereas this chemical energy is directly converted to electrical energy in a fuel cell or a battery. Now battery work out, whereas a fuel tank, fuel cell, or a combustion engine then work out. So you require input of fuel, then you have this fuel cell or your engine, and this is your output. So this is your schematic diagram. So now we will discuss fuel cell versus your solar cell versus your battery. So it is fuel cell versus solar cell versus batteries. Fuel cell, solar cell, and batteries, they all produce electrical power by converting either chemical energy, fuel cell and batteries, or solar energy, solar cells, to a direct current, which is DC flow of electricity. The key features of these three devices compared in using the analogy of buckets filled with water. In all three devices, the electrical output power is determined by the operating voltage, which is the height of water in a bucket, and current density, the amount of water flowing out the spigot at the bottom of the bucket. Fuel cell and solar cells can be viewed as open thermodynamic systems that operate at thermodynamic steady state. In other words, operating voltage of a fuel cell or a solar cell remains constant as long as we continually supply the fuel or the photons from an external source. So this is shown by the fact that the water in a fuel cell and solar cell buckets is continually replenished from the top at the same rate that it flows out the spigot in the bottom, resulting in a constant water level, which is a constant operating voltage. In contrast, most batteries are closed thermodynamic systems which contain finite, exhaustible internal supply of chemical energy. As these reactants deplete, the voltage of the battery generally decrease over time. This is shown by the fact that the water in a battery bucket is not replenished, resulting in a decreasing water level, decreasing operating voltage. With the time as the battery discharge, it is important to point out that the battery voltage does not decrease linearly during the discharge. During discharge, batteries pass through voltage plateaus where the voltage remains more or less constant for a significant part of the discharge cycle. This phenomena, captured by the spring shape of the battery, is called a bucket because. Okay, so this is your bucket approach: photovoltaic open system, fuel cell open system, and your battery as a closed system. Your photons, you given there's some losses, there's some energy electricity output, and this is the height of voltage remains constant. Here also height of voltage remains constant in a fuel cell. You have losses, you have electricity output. Here you give photons, here you give fuel cell. Then you have a battery, which is a closed system. Here, height of the voltage, it continuously decreases. Okay, so in addition to the thermodynamic operating differences between a fuel cell, solar cell, and batteries, figure 1.6 also shows that the fuel cell typically operate at a much higher current density than solar cell and batteries. This characteristic plays a great importance on the use of low resistant materials in fuel cell to minimize the ohmic, which is the IR losses. These losses, we will be studying about them more. So what are the basic disadvantages of fuel cells? Now, while fuel cells present intriguing advantages, they also possess some serious disadvantages. Cost is a basic barrier to the fuel cell implementation. Because of prohibitive cost, fuel cell technology is currently only economically competitive in a few highly specialized applications, example on board the space shuttle orbiters. Power density is another significant limitation. Power density expressed how much power a fuel cell can produce per unit volume, which is a volumetric power density, or per unit mass, which is gravimetric power density. Although fuel cell power densities have improved dramatically over the past decade, further improvements are required if fuel cells are to compete in portable and automotive applications. Combustion engines and batteries generally outperform fuel cells in a volumetric power density basis. On a gravimetric power density basis, the race is much closer. Fuel cell availability and storage pose further problems. Fuel cells work best on hydrogen gas, a fuel that is not widely available and has a low volumetric energy density and is difficult to store. Alternative fuels, example gasoline, methanol, formic acid, are difficult to use directly and usually require reforming. These problems can reduce fuel cell performance and increase the requirements for ancillary equipment. Thus, although gasoline looks like an attractive fuel from the energy density standpoint, it is not well suited to fuel cell use. Additionally, fuel cell limitations include operational temperature compatibility concerns, susceptibility to environmental poisons, durability under start-stop cycling. These significant disadvantages will not be easy to overcome. Fuel cell adoption will severely limited use unless technological solutions can develop hurdles to these barriers. So this is the list of the advantages and disadvantages. You can note down if you want to. The advantages are they're more efficient than combustion engines, as we have seen, as they directly convert the chemical energy to electrical energy and not by a long route. Mechanically ideal because they have no moving parts, good reliability, and long-lasting system. They're clean and silent operation. They're easy independent scaling between power, which is determined by the fuel cell size, and capacity determined by the fuel cell availability. What are the disadvantages? Cost is a major issue. Fuel availability and storage, because as we studied, they run on hydrogen fuel and hydrogen is very rarely available. Durability under stop-start cycles, low volumetric power densities as compared to batteries and combustion engines. So this is what are the advantages and disadvantages of the fuel cells.